McGill and B.Sc and M.Sc from in electrical engineering. He has more than 10 years of experience in the field of ITS and transportation safety. After finishing his Ph.D., Asad co-founded Bluecity Technology in 2018, a startup that developed an AI-powered multimodal traffic monitoring and data analytics platform powered by Lidar technology. The solution has been deployed at over 250 intersections globally, helping cities improve road safety and mobility. The company was later acquired by Velodyne Lidar in 2022 and merged with Ouster in 2023. So the session is going to be around 40 minutes. It's interactive. So I'm going to give you the floor. Thank you for doing this presentation for us.
No worries. Thank you for having me. So we had a quick introduction. So actually I moved to Canada in 2012 to start my Ph.D. and so my background was in electrical engineering. And I switched to transportation because that was always my passion, how we can make the road safer and more efficient. And that was the story of my master working on using reinforcement learning. It was back to 2008. AI was not like that popular that we have today. So I started working on coordinated traffic optimization as a part of my master thesis back to my country, Iran. And then I started PhD, and during my PhD I found that there is a big gap on technology to collect data, because when you're developing AI models, the first thing is that how you can collect data. And the data that you typically need for AI models is more advanced than the data that you can expect from an inductive loop at the intersection. And of course, it was really important to collect data in different weather and lighting conditions. And that's why, as a part of my PhD, I started looking at type of technologies existing in the market, like radar camera, thermal camera, and how we can fuse this. And then we found this gap of existing technologies are either expensive, especially if you want to bring all together as a monitoring system at the intersection. That doesn't make sense to put, let's say, $60,000, $70,000 of equipment at the intersection to get the data that you need. That was the story behind looking at LiDAR technology. Of course, when I started, it was back to 2017, I started looking at LiDAR technology. It was super expensive. The LiDAR that we buy today at, let's say, $4,000, $5,000 used to be $25,000, $30,000. But because of all the activities around autonomous vehicles back then, there was a path toward getting cheaper hardware solutions to make sense of having a purely LiDAR-based detection system at the intersection. And of course, we started as an intersection detection system, but now we expanded the use cases of LiDAR for stationary monitoring, not only for intersection, but also for highway management, ramp metering, ramp monitoring, one-way detection, and a lot of other use cases that I will talk about a couple of those today. I want to make sure that this session is interactive. Feel free to raise your hand if you have any questions. Stop me. So we can make it really attractive, so then I can answer any questions. So a little bit about Ouster. So Ouster is a LiDAR manufacturer, so co-founded back to 2015. And the focus of Ouster was building digital LiDAR technology. So for those who don't know about LiDAR, LiDAR stands for light detection and ranging. It's a technology that's widely used for autonomous shuttles, autonomous vehicle application, for mapping in 3D around the sensor. So, of course, you probably heard about Elon Musk not liking LiDAR because of the cost, which makes sense when you look at, let's say, 3-4 years ago. But now we have LiDARs that cost $1,000. So, and then there is a trajectory, that there is a path toward really making it sub $500 LiDARs down the road with the digital architecture and other type of designs that we see in the market. So Ouster is headquartered in San Francisco. We have a global team in different locations, including I would say probably most of our software team, which I think is around today we're around 25 to 30 people. It's based in Ottawa, Toronto, and Montreal. Montreal was the place that I started the company, and still we have a team there, but then we have also a team in Ottawa working on the software side of the solution. So Lidar today is used in many different applications. So it's not just autonomous vehicle. Today we have customer application for yard monitoring, for security application, for even like some military applications, industrial robotics. There are a lot of different use cases for LiDAR. And the reason is that for many of those use cases, you need to have a 3D perception around the LiDAR, or like the device that you put the LiDAR on. It could be a moving robot, it could be like an industrial arm in a manufacturing plant, or it could be places that you want to monitor objects, moving objects. It could be like security, it could be ITS, etc. And the focus of my team is to use LiDAR technology for stationary use cases, and that's the area that we build our software solution on top of our LiDAR, which Bluecity was part of that solution. This is basically just a drawing of how LiDAR technology works. Actually, I have one of them I brought with me so I can show you if you can see the size of it as well. So this is basically one of our LiDAR. It's 128 pixel LiDAR, which basically has 128 laser beam shooting 5 million times per second. And this is basically the way that we generate a 3D representation from around the LiDAR. And depending on the type of LiDAR, you can have, let's say, short-range LiDAR that is 10, 20 meters. It's mostly for robotic application. Where we have a mid-range LiDAR that we typically use for ITS that can go to 100, 120 meters. And then we have a long-range LiDAR that it goes to 200, 300 meters coverage area of those laser beams. So the design of our system, which we call it digital LiDAR, is slightly different than other solutions. So when you look at LiDAR products, there are different architecture of LiDARs in the market. Some of them are basically the laser beams that are analog components and they are rotating. Some of them keeping it solid state to improve the reliability of the LiDAR. But to get this 360 field of view, they put a mirror that is rotating. It's another type of architecture, but still there is a moving part inside it, which causes some reliability issue down the road, and of course maintenance. The design that we followed since the beginning of the company is, we call it digital LiDAR. So just look at how camera technology evolved over time. So from analog cameras that you have a lot of moving parts, a lot of analog components, which made it really difficult to scale, specifically on the resolution side. And also manufacture, the design will cause like some manufacturing issue as well for scale. And then after analog cameras, we have digital cameras that basically it's a CMOS, everything on a single board, no moving part, and then it basically with digital technology, you just follow Moore's law, and you improve your processor, then you have enhanced performance of the system. And that's exactly the path we are taking with our digital LiDAR. So what you see here is basically the LiDAR. We have this part of our LiDAR, which is transmitter and receiver sitting on a single board. And then on the right side, you see our array of laser beams that are shooting. They're at the same time. There's no calibration required for those because they are all coming from one single chip. And then the receiver. And to achieve this 360 field of view, the design is that those solid-state components are sitting on a turntable, which is basically rotating with a motor. And then that's the way that we can actually get the 360 field of view. Sure.
Can they see through objects? For example, through walls or
No. LiDAR is basically using laser beam, so it requires line of sight. So, yeah.
Are these LiDARs meant to be mounted on static objects or?
No. So the ITS solution is for stationary or static objects. but again, we have many customers that they are using for autonomous shuttles, for like robotics, on robotic arms, on the basically warehouse monitoring systems that they are basically on trucks and they are going around. So, but the focus of our software solution on top of it is only for stationary monitoring.
Right. And a follow-up question for the companies that use these for, let's say, trucks.
Yeah.
How much of the blind spots are you able to reduce with one LiDAR?
So, blind spot around the object, you mean?
Yes.
So it really depends on what kind of LiDAR they use. Some of them, they are mostly interested about long range, so which means that you have narrow field of view, you're going to have a big blind spot. So they want to look at, let's say, pedestrians at 100, 150 meters or 200 meters. This is more for ADAS systems. But for some like surrounding systems, so they use like our 90-degree field of view LiDAR, which is a shorter range. So then you basically have almost zero blind spot around the vehicle. Okay, so let's talk a little bit about the our Ouster Bluecity solution. The goal of Bluecity is basically build a turnkey solution for ITS, and that was the company that I co-founded called Bluecity. And the idea of using LiDAR, as I mentioned, is to collect reliable data in different weather and lighting conditions. So we can use it for a variety of different applications. And of course, we have several projects working with universities and leveraging our APIs. We designed our API architecture in an open API architecture, so which means that we can easily provide access to different layers of data that we generate, either at the intersection or from our cloud platform to our partners, so they can build their own applications on top of our solution. So the reason that the LiDAR can be really reliable in different weather and lighting conditions is because of the fact that LiDAR is using its own source of light. It's not like a camera that you're dependent to the ambient light. So it basically laser beams. So that's why under rain, snow, all those scenarios, LiDAR can capture reliable data. And then one of the other benefits of LiDAR that you're going to see, I'm going to all connect to a couple of our deployments to show you some live data. Basically, it's the privacy protection. It's while you can capture, detect, and classify different type of road users, with LiDAR you cannot collect any biometric data like skin color, license plate, anything that is PII. So with this, it's added value for a lot of DOTs that they typically get a complaint from citizens why you're putting camera everywhere. So for some cities, it's really important, especially like in Europe because of the GDPR Act. They're really sensitive to camera-based system. And just give you an idea, if you want to put a camera in a couple of countries in Europe, it takes about 1 year to get permission. So you need to go through the whole lengthy process. But with LiDAR, you can actually bypass that because there's no way of collecting any personal information. And then one of our goals was, yeah, go ahead.
Yeah, sorry. I had a question. So when you're classifying, for example, different vehicle types, would you say under clear conditions that you would get more accurate results than using a camera, or?
So basically, LiDAR is almost independent from lighting condition. So if you,
yeah. I mean, under normal lighting conditions, like, would you get better accuracy when classifying different vehicle types compared to a camera, or?
I would say it's very similar. I'm not saying it's necessarily better than camera, because if it's a really good weather condition, camera works really good. So, and especially with all the data that is available, open source data, so deep learning models to capture more classes is possible with camera. It's easier, but it's almost, I would say, the same level of accuracy. And then one of the other benefits that LiDAR brings, and you're going to see, is with LiDAR you can precisely geolocate object, which means that you can get X-Y coordination of the object and build a, it's called, for V2X application, called basic safety messages that you can broadcast to connected vehicles, BSM or PSM. And that's the part of the solution that can generate insights about like first object detection and then generating BSM and PSM and broadcasting this to connect the vehicles. This is another value. If you want to look at same application from using a camera or radar, you need to first calibrate 2D to 3D to basically measure the location of the object. But this is not the case with LiDAR because it's always 3D and you can get the 3D perspective. Okay, so yeah, the solution that we're talking today about, we have deployed, I think so far it's over 300 deployments. One of the biggest projects that we have is in Irvine. It's 25 intersection, just one city. And it's very interesting because it's in collaboration with the University of Irvine. And what we're doing there is basically they're using our real-time API and they build a speed advisory and they send this information to vehicles. And then when you are going through the arterial, the vehicle gets a speed advisory to drive with a speed that is suggested by the system, which basically optimizes travel time and minimizes number of stop and go for the vehicle. So in that case, they can reduce the energy efficiency by, improve the energy efficiency by 25%. So when you look at it at the scale, it's really impressive. So I mentioned about this project because I strongly believe the collaboration with universities, because the type of data that we can generate with this type of systems is beyond the capability of existing ITS like traffic controllers to ingest this data. Still, we're talking about traffic controllers that they are just looking at stop bar detection without looking at how many cars are within that zone. So again, like all the trajectory-based optimizations that we see in the research, we don't have any of those in practice. So that's why I think there's a lot of opportunity working with researchers on those aspects. So the solution has basically two components. One is the detection system that has the, let's say, edge computer, perception software, the actuation logic, that everything is going inside an edge computer. And the goal is to run everything in real time, independent from network infrastructure, so then we can basically meet the basic use cases of the ITS, which is traffic actuation. And then the data analytics platform that I'm going to talk about a couple of those analytics that we provide as a part of our solution. Again, on the analytics side, we try to open APIs. So, like for example, when we detect near misses, we can share this information with our research partners so they can basically pull this data and make sense of this data, because our company is focused on generating data. So working with researchers can open a lot of opportunity for us to basically build more in-depth analytics on top of the data that we're generating. So as I mentioned, today we use our solution for two primary use cases, for intersection management and highway. For highway, I'm going to probably skip the highway part of it because of the time, but today I will focus on the use cases around intersection. But in general, highway management involves ramp metering, wrong-way detection, stop vehicle detection and warning. Those are the use cases that our system being used today for the highway portion of it. Any questions so far?
Can you elaborate on the type of data that you get? For example, from cameras, we get videos on like their maybe pixels, images and pixels, but for LiDAR, is it like CSV file, JSON file, what sort of file?
Yeah, I will explain in this live view. So I'm connected at this intersection to, this is one of our projects, this is in Montreal. And I'm on the VPN so I can connect to the edge computer. So what you're seeing here is live data coming from intersection. This is the data that is already processed by our perception. And data is UDP packets that generates raw point cloud data. So let me just make it bigger. So what you are seeing here is raw 3D point cloud data generated by the LiDAR. So there's no perception on top of it. This is just simply raw data. So you can see that we have two LiDAR at these two locations. And then one of the benefits of LiDAR is that you can easily stitch point cloud coming from multiple sensors. So So then you can get this full picture of the intersection in 3D or whatever that is in front of the sensor. So every single dot that you see on the ground, and this is one laser beam hitting to the ground or object, or and then based on the reflection, it measures the distance. And that's why we can basically build this 3D representation. When we are zooming out, it looks like that the LiDAR is installed, I don't know, 20, 30 meters, but the reality is that this LiDAR is installed around 4 meters using existing poles. So it's really easy for installation, but still you can get this rich information.
I have a follow-up question. How do you feed the data to a model? Like, is it, for example, for a deep learning model, is it treated like pictures?
No. So we voxelize the point cloud in different voxels, and then we pass it to our deep learning model, and our perception is using deep learning model. We run our perception on 3D point cloud, not on the 2D. So it's like the first version of our perception was using the same thing that you mentioned. It's from bird's eye view, looking at LiDAR as a image. But then we developed our new perception that is running here. It's only based on the 3D point cloud.
Thank you.
So how does LiDAR really handle like extreme weather conditions such as tornadoes or hurricanes?
Yeah, I have a slide for that, so I can quickly show you. So we had a couple of use cases, or tests actually we did. I think 2 of them were in Ottawa last winter that we had a snowstorm. So this was one of the cases. Before talking about this, I want to mention about this 3D, the 2D view, and then I will get back to this one. So what you're seeing on top of this view, I'm just going to the viewer mode, it's basically here you have a some sort of camera view from the intersection, but it's actually all generated by the LiDAR. There's no camera in our system. But as you can see, it's very clear like what's happening in the intersection, at the intersection. And then it's 3D, so you can actually rotate it and see like all the 360 field of view of the LiDAR. This area is black, of course, because there's a pole behind the LiDAR. But this is all purely generated by the LiDAR. And the reason is that we use, this is a part of our the design architecture, which typically you don't see those from any of other LiDARs. And the reason that we can do is our receiver is not only receiving our laser beam reflection, but also it receives ambient light as well. So that's why we can capture near IR images from the intersection. So we downsample that picture to 1 image per 3 seconds for saving bandwidth. Since we're not processing that, it's just purely based on 3D. But as you can see, it's clear enough. You see there are 3 pedestrians. Even if you want, you can switch to the other LiDAR because we have 2 LiDAR at this intersection. Okay, so now going back to this, I'll get into the details of the live view, but let's talk about this first. So this is one of our current deployments. It's with City of Ottawa, and it was under a snowstorm. And as you can see, those white dots that you see, it's basically reflection of laser beam because of hitting to the snow. It was under snowstorm. And then when we pass this to our perception stack, which we use deep learning, we see this clear view of the infrastructure. So basically we address that with this.
Yeah, so, I'm sorry.
Sure.
So what I'm asking though is like, for example, during a tornado, right? A bunch of tree limbs can kind of go in front of the camera or something like that temporarily, like temporarily blinding it. Is that really, like if I was relying on that for some data, would you all be able to communicate that
Yes,
the sensor is inaccurate right now?
It does. So we have a feature called LiDAR blockage, which means that whenever there's something blocking the LiDAR for any reason, it could be a bird or it could be a tree or something, so then our customers get a warning that the LiDAR is blocked.
Okay.
Yeah, there's a part of our API that generates that warning. So,
Quick follow-up question about this. So what would happen if the rod or the pole started oscillating?
So it's of course like an area that we are covering, let's say 50, 60 meters around the LiDAR. It's not really that important. It's not affecting the system performance. And one other reason that I would say like benefit of LiDAR is that If you use a fisheye camera, for example, you put it around, let's say, 10 to 12 meters above the ground to leverage the full 360 of the fisheye camera, which makes the system subject to, like, in windy environment, so it's going to move a lot, because the higher you go, like, the chance of moving is higher because of the wind. For our case, since we're using, we put the LiDAR around 4 or 5 meters, the system is not moving that much, even like in bad weather. Actually, we have a couple of projects in Florida. 2 weeks ago, there was a hurricane in Florida, and we were monitoring our system. They had a camera was moving, so all the virtual loops were actually moving, and some of them were actually on the crosswalk, on the sidewalk. But with LiDAR, since the height was lower, and then we have 3D perspective, so it's not that sensitive. However, like if you go, let's say, 80, 90, 200 meters away from the LiDAR, even a small movement makes a big difference. So, yeah.
Is there a way to like fix the redshift or the blue shift with the beams in this case?
No, I don't think so. That, you mean like automatically adjusting the? I haven't thought about this. No, at least for now, no. So if LiDAR moves for any reason, the whole perspective will move. So, yeah. Sure.
About your tool that you just showed, the intersection in Montreal, is it real time?
Yes.
So like, how much of a lag does it have with the actual real time? Is it like in the matter of seconds or like milliseconds?
So if you connect to our edge computer or use fiber network, so LiDAR is running right now 10 frames per second, which means every 100 milliseconds we generate a full frame of the LiDAR. And then we pass it to our perception pipeline, which is running on the edge computer, and that's running in real time. Means that after receiving the first frame, so we process it within the 100 milliseconds. Depending on the area that you want to cover, it could be like, let's say, 20 milliseconds that we need to run the full perception pipeline and generate objects. If it's a big area, we need probably 90 milliseconds, but always we set the coverage area in a way that it's in real time.
So a follow-up. So it is possible that we use LiDAR as an augmentation to the onboard sensors of the CAVs.
Yeah.
Get the data transmitted to them in real time?
Yes, so I can quickly jump to that slide that I wanted to show. We have actually, we did a couple of projects about this use case. So this was a project in Finland, and basically the idea here was our system was connected, we had a sensor at the corner of intersection, and it was generating object location, so pedestrian, cyclist vehicles. And I'm just going to pause it. So on the left side of this intersection, we have our LiDAR installed at the corner of intersection. And every 100 milliseconds, we are generating location, extracting location of all the objects, including pedestrian and cyclists. And then there is a protocol called SAE-J2735, which is a standard for how connected vehicles can ingest the data. We put the object location into that format and we broadcast this information to connected vehicles using roadside unit. And what you see here is this car had an onboard unit. This was our pilot car, and as you can see, there is a warning that there is a cyclist approaching into the intersection. But as a driver, you don't see any cyclist. The cyclist is actually behind that building. And if a couple of, like I would say, like 1 second later, so you're going to see there was a cyclist. That was the cyclist that was captured. Since everything is running on the edge computer, so you can meet that latency of, let's say, 300, 400 milliseconds that is typically required for V2X use cases. There is no cloud involved in this process.
But if we want to go further than just an alert, you like say use the LiDAR on the roadside as the primary source of surveying the surrounding area and like using it for the autonomous driving. Will that be possible?
Like sharing this data with autonomous vehicles, or?
Don't install any sensors on the autonomous vehicle. Use the sensors that are on the roadside, and those sensors be basically the eyes and the ears of the vehicle, and compute the data, send it to it, and like use that as the source of tunnels driving.
Yeah, well, I mean, it's not that you can always just only look at intersection, because first, you don't have all intersection equipped with LiDAR. Second is that if the car is approaching intersection from, let's say, mid-block, for example, the data from the intersection might not be useful. However, the data is there, so you can generate the data and share it with connected vehicles. And it doesn't necessarily need to be using roadside units. We have another project with Verizon that we use virtual RSU, basically using their 5G network to meet the latest requirements. So, yeah.
Thank you.
Okay, going back to this slide view. So, what's happening here is that let me just make it smaller a little bit. So our perception is basically detecting and classifying and tracking objects. So, and it's happening, as I mentioned, in real time. And since we're staging point cloud coming from multiple sensors, we basically can minimize occlusion. So if an object is occluded from one LiDAR perspective, the other one is capturing that. And there is another benefit of LiDAR compared to like directional detection system like radar or camera, is that not only you can look at the approaches, but also you can see the trajectory of the vehicle. So if I enable the trajectory to just show the trajectory data. Okay, so I'm just enabling trajectory and disabling background. So what you're seeing here is basically the trajectory of all the objects, and this is generated by our tracking algorithm. So whenever we detect an object, I'm just going to pause it. We extract all the metadata related to the object. So if I select these and then zoom in, you can see that we have the vehicle tracking ID, we have the velocity heading of the object. We have the lifetime, which is showing how many seconds that object is being tracked by a tracking algorithm. And then also, of course, like length, width, and height of the object. And then there are some other metadata that it's not visible here, like subclasses like tractor, trailer are classified as separate objects with the system. One thing that I want to also mention is it's very important benefit of LiDAR over camera is that you always have 3D perspective, which is important for several different applications, which one of them is, for example, if you want to run your safety analytics based on calculation of time to collision or post-encroachment time, you need to have a precise bounding box around the object. Which means that if you look at the camera from the 2D perspective, the bounding box might be shifted depending on the angle of the object. But that's not the case. As you can see, all those dots that you see are basically the point clouds around the object, and the bounding box around it, which is generated by our deep learning, it's actually matching the object's the boundaries as well. And this is the same case for other objects that you see at this scene. Which makes it really interesting when it comes to the near-miss detection and those type of use cases.
We can see that some of the cars have less point clouds on them. Is it because we're less confident of?
No, the point cloud means that there is less laser beams hitting to that. But as you can see, even for this car, that we only have probably a couple of point clouds, still our deep learning can extrapolate that and get the bounding box accurately. So. We trained our deep learning probably over, it was an ongoing training over the past 3-4 years. I think we trained over more than 200,000 frames that was annotated manually to train our deep learning model. So, yeah.
So for the ones that they have less point clouds, is it solely based on the deep learning model that tells whether it's a car or maybe a tricycle?
Yes, it's purely based on deep learning. Let me see if I can enable it quickly. So if you look at our in the developer mode, I can enable some other metrics, div heading, classification, confidence, and subclasses. So whenever we detect an object, our perception generates a confidence level for that object classification and detection. So for example, if I select this, I'm expecting this one to be lower. So this one was 98% confidence for this as a passenger vehicle that was detected. It probably is lower than for this object because of it's like 83%. So more points you get, the confidence of the object classification is higher. So
One follow-up question, can you tell the occupancy of each vehicle?
inside the vehicle,
Yeah.
no. It could be like if you really face the LiDAR toward the vehicle way close. Like there were some discussion about using LiDAR for HOV lanes that you want to see the inside the vehicle, but we are not working on that. Probably, maybe the thermal camera might be a better solution for that. So yeah.
Sorry, can I ask what are the different classes that you can classify the vehicles?
So right now we have pedestrian, we have cyclists, passenger vehicles, truck, buses. And then for trucks, we have tractor and trailer as separate classes. And then for each trailer that we detect, we have length, width, and height of the object, which means that potentially some subclasses can be defined. With the previous version of our perception, we had tram as well. So with the project in Europe that we needed to classify tram. But once we move to this high resolution LiDAR, we don't have training data yet for tram. We're deploying one of our upgraded system at City of Toronto. Hopefully that could be the area that we can get some tram data sets for training.
Okay. And the models are trained in-house, so there aren't any available models?
No, it's all we built from scratch. Okay. Of course, like all the models are based on like some categories of existing models, but we definitely needed to tweak it to match our resolution as well as like training on the data set that we collected.